In this video, I'm going to talk about systematic naming for oxidation numbers or compounds with which have elements in it which have variable oxidation states. And before I go into that, what I want to do is cover the idea of Roman numerals, because if you take a look down here, these compounds and the ions and these things, they have Roman numerals in their names, and so before I go into actually trying to figure out what that stuff means, just in case you don't quite understand the concept of Roman numerals, I want to just briefly explain it here, maybe from 1 to 10. Okay, so Roman numerals are basically symbols which are used to represent numbers, and the system basically works like we start with an I which represents equals 1, and then we have an II which equals 2, and then you can imagine we have an III which equals 3, and then this doesn't actually continue exactly the same way. So if you can imagine, when we have all of these I's, like a tally, often when you have a tally, you usually go like I, and when you get to 4, you sort of cross it off like that, just to show that it's now 5. So that would be 5. So we have a similar sort of thing in Roman numerals. So we don't just continue going I up to maybe 1,000 or something. We have ways of summarizing the increasing numbers. So what we have here is actually a V with an I before it, and V actually is the symbol which represents 5, whereas I is the symbol which represents 1. And in this particular case, the I is before the V, and I is a smaller number than the V. And in Roman numerals, what this means is the 5 minus the 1, since the 1 is smaller and it's before the V. And so therefore this is equal to 4. And so, as I said, V is equal to 5. So if we have a V here, this would be 5. And then the symbol for 6 is basically this but flipped. So the V is now in front of the I, and since the V is a bigger number than the I, we don't subtract I, we instead add the I to the V. So we get 6. And this continues basically if we go up to 8. So VII would be 7. VIII, like Henry VIII, would be 8. And when we get to 9, what we can do is we can use a similar sort of system like we did here, except 10 would be represented by an X. So X would represent 10, and we'd have an I in front of it, and I is a smaller number, so that would be 10 minus 1, and that would give us 9. And then we'd have an X, which would be 10. I'm not going to go beyond 10 because usually you rarely get oxidation numbers which are sort of in the range of 9, 10 and above. Usually get them in the range more up here. So now why have I talked about these different symbols? The reason why I've talked about these symbols is, let's consider the compound iron oxide, right? Iron oxide, we'd write, I'll do this in a different color. I'll use orange. There we go. Iron oxide. If I was to say, write out for me the formula of iron oxide, what would you write? Would you write FeO? Would you write FeO2? Would you write FeO3? Would you write maybe Fe2O3? What would you write? Because these are all forms of iron oxide, so which one is it? So it's, as you can see, it's quite hard to tell what the compound is from this name, where it's just iron oxide. Whereas if we were to put some sort of indication in this name of maybe something which tells us the ratio of iron to oxygen atoms, we would be more able to write out an accurate formula for what it actually is. So let's say we were to put an iron oxide in there, and this I in this case would represent the oxidation state of iron in the compound. And the reason why we can write it like that, I don't know if iron oxide exists, this is just an example. The reason why we put the I there is to show the oxidation number of iron, and here's why. So the reason why we do that is now we can say, okay, when we construct the formula for the compound, the iron in the compound must have an oxidation state of 1. And we know, since it's iron oxide, there's only 2 elements, iron and oxygen. So let's write out the iron, it would be Fe, and oxygen. So right now, if we look at this, oxygen is combined right now, and if we look across at the periodic table, we can see quite clearly that iron is here and oxygen is here. So oxygen is more electronegative than iron, and so oxygen is going to have its regular oxidation state, which is 2 minus. And just before I go on, I just want to say these elements here. These elements here in this region are commonly referred to as being the transition metals. And transition metals are basically metals which have variable oxidation numbers. In its simplest term, they have oxidation numbers which can vary, and there are other elements which can have variable oxidation numbers, like these ones and some over here, but just focusing on these ones here, these elements have variable oxidation numbers, and some of the ones around the sides as well, but iron is one of them. And so if we were to have different amounts of oxygen, the oxidation number of the iron would change depending on the number of oxygen. And so in this particular case, we can see iron has an oxidation number of 2 plus. Since this is a neutral compound, this would be 2 plus. But we know that it's iron dioxide, so we know that this must have the oxidation state of 1 plus. So in order to make that happen, we added 2, and so this is now iron oxide with iron with an oxidation number of 1. And so now this we know is what iron oxide would probably look like, Fe2O. And so that's why we use this symbol, these Roman numerals in the formulas. So if we were to have maybe iron 2 oxide, we'd have maybe FeO. So like the first one I wrote. So yeah. So now I want to go through a couple of examples of compounds, we have their systematic names up there, and we're going to try and figure out the oxidation states of the different of the elements in those compounds which have variable oxidation states or oxidation numbers. In this video, I'm not going to go into actually how you get the formula and turn it into a systematic name. Rather, I'm going to, in this video, look at the systematic names and finding out the oxidation numbers of the variable oxidation number elements. So the first question says, work out the oxidation state of the elements in the following species: iron in iron oxide, and so iron. Yeah, I won't read them all out. I'll just do the first one first. Iron and iron oxide. Okay, so this is just after the iron, so we know this is the oxidation number of iron, and so therefore the oxidation state of iron, or oxidation number, is 3. So I'll just say oxidation state. It's basically the same as oxidation number. So okay, so the oxidation state of sulfur in sulfate Vi ions, as you can see, Vi is 5 plus 1, so that's 6. So therefore the oxidation state of sulfur is 6. Okay, find the oxidation state of phosphorus in phosphate ions, and this is contains phosphorus and oxygen, and so well this is an I, so phosphorus has an oxidation state of 3, and the last one. In the last one, we have iron and sulfur. Iron sulfate, so that would probably be Fe something, or yeah, SO something. So in this particular one, it's iron and sulfur, and yeah, so iron has a 2 there, so that shows us that iron has an oxidation state of 2, iron 2, and sulfate has an IV. And as I said up here, IV basically means 5 minus 1, which is 4. So that would be sulfate. Sulfur has an oxidation state of 4. And so that's how we go about working it out. In the next video, I'll look at converting formulas into systematic names. So yeah.